Or
You
would
were
it be,
live. You were live on audio.
do
Would you say
you,
some?
much astronomy, very wow. Look at all these cool talks. So sick. Yay. Yeah. Look at all these stars. We have so much talk to talk about. I'm so good at this.
Live on audio.
Yippee.
Going?
Oh.
How are you all doing?
Well, welcome to.
My first time I've been able to make it through these.
Well, it's great to have you. Yeah. One of the rules: no prizes for astronomy department people at trivia. You can compete, but
That's fair enough.
we sometimes have, especially when one person and like a couple of their friends come.
Yeah.
Have team
All right. All right. Hello, everyone. Welcome to Astronomy on Tap here. I'm Barbara. I'm going to be your host today. So first of all, we're going to start off with some Astronomy on Tap trivia. So if you want to participate, we're going to have 10 questions. We have papers and our little golf pencils up here. So if you want to participate and try to win some of our prizes today, grab one. You can participate by yourself, make a little team. All right, yeah, come on down. All right, any last takers? Okay, well, welcome everyone. We're excited to see you all here. So without any ado, let's start off with some trivia. Okay, our first question is not visible. There it is. All right. So our RR Lyrae stars primarily found in stellar populations. Are they young, metal-rich disk stars? Are they old, metal-poor population 2 stars? Or are they C, massive O-type stars? Or D, newly forming protostars? I'm gonna give you all about a minute to think about each question before moving on to the next one. And question 2, why are RR Lyrae stars especially useful for mapping the Milky Way? Is it because A, they are extremely massive? Is it B, they emit strong X-rays? C, there is a direct relationship between their period and luminosity? D, they orbit the galactic center rapidly? Which one could it be? All right, question 3. Are these RR Lyrae stars typically have pulsation periods of, is it either on the scale of minutes, on the scale of hours to about a day, years, or millions of years? All right. Next question. RR Lyrae stars are most commonly found in which part of the galaxy? Is it in the spiral arms, the galactic halo, in the planet-forming disks, or in black hole accretion disks? And question 5. If an RR Lyrae star appears fainter than expected, the most likely explanation is either A, it has stopped pulsating, B, it is closer than we thought, C, it is farther away than we thought, or D, it has become a neutron star. All right, next question. The boundary between asteroids and comets is best described as A, a strict size cutoff, B, a difference in orbital speed, C, a distinction based on volatile content and activity, and D, whether the object has a tail. The next question, an object classified as a near-Earth asteroid must A, currently be inside Earth's orbit, B, cross Earth's orbit, C, have a perihelion distance less than 1.3 AU, or D, be gravitationally bound to Earth. All right, question 8. The primary long-term threat from a large asteroid impact comes from either A, the immediate fireball alone, B, the Earth's magnetic field disruption, C, global climate effects from dust and aerosols, or D, loss of ocean tides. And question 9, many asteroid impacts are avoided because A, Earth's gravity pushes them away, B, Jupiter ejects all dangerous objects. C, most near-Earth objects are small and burn up in the atmosphere. Or D, the moon absorbs most impacts. And last question, modern asteroid surveys improve detection efficiency primarily by not telling us anything. It's back. All right, our options are atmospheric turbulence, telescope mirror size, object brightness and trailing, or D, computer processing speed. All right, so now I'm going to go back to the first question, and then we're going to go a rapid fire just so that y'all can check your answers and make sure you've got locked down the right ones. Hi, Sam's mom. Oh, wait, the camera's over there. All right. That is it for our trivia. So once you've locked down all your answers, if you could bring them back up to our table down here, we'll collect them along with the golf pencils, and then we'll get started. Thank you. So it is my great pleasure to announce to you today our first speaker, who is our very own AOT organizer, Sam Charney. He is a second-year graduate student in the astronomy department at UW, who studies near-field cosmology and is really excited to tell you guys today about RR Lyrae stars. So give a round of applause for our speaker, Sam Charney. I give you this. Thank you.
All right. Thank you for that great introduction, Barbara. As some of you may know, I'm usually the one hosting the trivia, but whoa, that's very scratchy. Farther away from my face. All right. But this time, since I was giving a talk, Barbara kindly agreed to host the trivia so I don't explode my voice doing trivia instead of giving my talk. So I apparently am exploding other things, and I can't give my talk yet. But welcome, everyone, to Astronomy on Tap. I'm Sam Charney, as Barbara said. I'm a second-year graduate student in the University of Washington's Astronomy Department. And you may have seen the word RR Lyrae a lot in the trivia section. I will be telling you all about RR Lyrae stars and how we can use them to do really cool things. So the real title of my talk is Mapping the Milky Way with Pulsating Stars, but I needed a fun little pithy short title at the beginning, which is Our Galaxies Pulse, because they're pulsating stars. So the title of this talk has three main parts: mapping the Milky Way with pulsating stars. So let me break that down for you. No, not like that. Let's try that again. All right, pulsating stars are stars that pulsate, much like the name implies. And there are several main types of pulsating stars. And when I say that a star pulsates, I mean that it literally gets bigger and smaller over time. It gets bigger, and then it literally shrinks in size, and then it gets bigger again. They are pulsating because they have pulses running through them that make them get bigger and smaller and bigger and smaller. And there are two main types of pulsating stars. There are RR Lyrae type stars and Cepheid type stars. You may have heard about Cepheids before because Cepheids are very popular in astronomy and they get brought up a lot, but I think RR Lyrae are cooler, and I'm going to tell you why that's the case. And also, when these stars pulsate like that, you can imagine that they change in brightness too. When a star gets bigger, it gets brighter, and when it gets smaller, it gets less bright. And these stars are incredibly useful for astronomy because of their period luminosity relation. This is a really big fancy name for the fact that if you know how quickly the star is pulsating, you can figure out how bright it really is. And that is super important because in astronomy, it's really hard to figure out how far away things are, because we're basically looking at a two-dimensional sky, and it's really hard to figure out how far away things are just by looking at them. It's like if you had a piece of paper and poked a bunch of little holes in it and are trying to figure out which one is farther away. Well, they all look like they're the same distance from you because that's what it looks like, but really they have distances because space, believe it or not, is three-dimensional. I know that's maybe hard for you to believe. So we can get the period of these stars, which is how fast they go in and out, and then that directly relates to their true brightness, how bright they actually are. If you look at this plot on the slide, you can see RR Lyrae down here. They have much shorter periods and are much fainter, and the Cepheids are all the way up here. They have much longer periods and are much brighter. And once we get the luminosity is the true brightness of a star. We know how bright it actually is, and we know how bright it looks from our perspective. And we can combine those two to figure out how far away it is. Because if you know how bright something is supposed to be, and you know how bright something looks from where you are, you can do some math to figure out how far away it is that would account for that change in brightness. And generally, things get less bright the farther away you get from them. So this helps us really place where things are. This also has led to these kinds of stars being called standard candles. because there's this relation that exists and allows them to be used as a standard sort of measuring stick for where things are in space. But we really care about RR Lyrae because RR Lyrae are smaller, which means they're more common, and they also have a shorter period. So when we look at how things are changing over time, we look at something called their light curve. Light curve is a sort of general term for a thing that shows you it is a curve of the light from the star over time. This is also what's called time domain astronomy, because time is the domain of this plot. Domain is the x-axis, and as you can see, well, maybe not, because this says phase, but this is time. Phase is a very particular kind of time where we basically take a long series of data from one star, and we find the period or we know the period, and then we fold the data over itself in order to line up all of the different phases. And this is super important because if we don't do this, it looks like that. And that is impossible to do anything with. You look at that, and you really can't tell me anything about it except that it is changing. Something for sure is happening here. But we take this data, and then we just fold it over itself a bunch of times, and all of these points have shown up in a different part of the star's period cycle, and then it looks like it's kind of like this. This is a very nice drawing of what it would look like if you had one point like every tiny spot, and this is generally the shape we expect to see from RR Lyrae specifically. And so every light curve you'll see has some kind of time on the x-axis and some kind of magnitude on the y-axis. And again, it shows you how the star's brightness is changing over time, whether or not it's phase folded. But phase folding is super important so that we can actually see what's happening, because again, otherwise it looks like this. So, one of the first big questions is, why RR Lyrae specifically? Cepheids are brighter, so it might be easier to see them from very far away, and that is true, but RR Lyrae are much less massive than Cepheids, and so they're much more common. This is a really old plot from a fairly old paper, but this is showing you basically how many stars there are per mass of star. So if you just look at this curve, ignore the second one, that's for a different reason, you can see that once you hit about 0.3 stellar mass, you get a lot of stars, and generally, as your stars get bigger and bigger, you get fewer and fewer of them, because it is harder to make big stars than it is to make small stars. And so this red line here is the mass of RR Lyrae, which is basically the peak of this function, and then this greenish tealish line is the mass roughly of Cepheids. And so there are many fewer Cepheids than there are RR Lyrae because RR Lyrae have lower mass. So there are more of them, and so they can better help us map things out. If you were trying to drive between two places and you only had like every third instruction, you probably would take a long time to get there. But if you have every instruction along the way, you're going to have a much easier time of mapping out where things are going. RR Lyrae also have a shorter period than Cepheids. Their period, here is a trivia answer, is on the scale of a couple hours to about a day. This is really short as things go in space. Generally, things in space are really big and really slow. Like, the universe is billions of years old, some stars are millions of years old, our planet is billions of years old, but these stars, over the course of a day, if you think back to that animation from the first slide, they go in and out and in and out over the course of one day, which is really fast. And it means that we're much more likely to see them changing. Because they change so much more, if we take a picture at a star at random times, we're probably going to catch it doing something cool because it does cool things more often. This also makes them better for this kind of thing than Cepheids. They are also old metal poor stars, which means that they've spent more time sort of dispersing throughout the galaxy, and we'll find them in globular clusters and halos of the Milky Way. This is now the Milky Way part of the talk. You may recognize this. This is an artist rendition of the Milky Way. And the important parts of this are these dots, which are globular clusters, and this sort of very faint diffuse circle, which is the halo of the Milky Way. And these are parts of the Milky Way that are not like directly in the super dense middle part and are much more spread out, much more diffuse. And these are generally much older and much more metal poor. And when I say metal poor, astronomers basically, since most things in the universe are made of hydrogen and helium, a metal in astronomy is anything heavier than helium. So every single thing that's not helium or hydrogen is a metal. Oxygen, that's a metal. There are many, many metals, and that's just everything heavier than the main two gases. So when we say metal poor stars, that means that they have fewer interesting things going on inside of them besides the pulsation in terms of elements, and they are older, so you'll find them more often in these big outer parts. So if we want to map out parts of the galaxy that are really hard to see because they're really faint and far away, these stars are a really good bet because you'll find them in these regions. So you saw an animation of what an RR Lyrae might look like. Now, what actually is RR Lyrae? What does that mean to say something is RR Lyrae? So this is the variable star RR. It's right here. It's really blurry, but I swear it's there. And this is the RR star in the Lyra constellation. This is a very small and not very well-known constellation in the shape of a lyre, hence the name Lyra. It's most well known because it has the star Vega in it, and Vega is pretty bright. And you can see the RR star is tucked away over here. It's near Lyra. And so this is the sort of prototype RR Lyrae star. It is the brightest one. It's the first one we found. And since it was the first one we found, all future stars that looked like it were given the name. So these are all like RR Lyrae type variable stars. These are pulsating stars that look like RR Lyrae stars. This is also the point at which I get to complain about astronomical naming conventions because they're so bad, and I'm required to do it at least once a talk. So you may say, Sam, what does it mean for it to be the RR star in Lyra? Well, let me tell you. The variable stars, the very first variable star you find in a constellation is labeled R, that constellation. Not A, not alpha, R. So the first variable star in Lyra is R Lyrae. And they go through, S, T, U, V, W, X, Y, Z. And then once you hit Z, you start back over at the alphabet, but not at A, of course. No, you wouldn't go back to A. You go back to RR, of course. So once you hit Z, Z Lyrae, now we're at RR Lyrae. So this RR Lyrae is the R, S, T, U, V, W, X, Y, Z. This is the 10th variable star in the Lyra constellation. And also, of course, this is the Lyra constellation, so you can't just be RR Lyra. No, it's RR Lyrae because you have to have the possessive form of the constellation because this star belongs to the Lyra constellation. So if you see something that's like Beta Orionis, that's in the Orion constellation, it belongs to that constellation. It is the beta star of Orion. It is Orion's second star. And then, gets worse. Just you wait. You go through RR all the way down to RZ, then you start back over at SS. You can't have, SR, no. Because the second letter has to be farther down the alphabet than the first letter. So SR is not allowed. VR not allowed. So we go, SS, ST, SU, SV, down to SZ, then TT, TU, TV, so on and so forth. Eventually you hit ZZ. And you might, at this point, give up. But no. Now the astronomers have decided that, we're going to use all the letters now. Now after ZZ, now you go back to AA. So then your AA Lyrae star is like the 50th or something variable star in this constellation. And then you go down to AB, AC, AD, and so on and so forth, to AZ, then BZ. And then once you hit, your last one is going to be QZ. Oh, also, you skip J for some reason. I don't know why we're skipping J. Just J, not I. I would make sense. I looks like a 1. We skip J. And then once you hit QZ, then we just start giving you numbers. We give up. This is the variable star. It's the 382nd variable star in this constellation. Okay, sorry, rant over. This is just, I complain a lot about this because it's annoying. Anyway, RR Lyrae, the first one of this type discovered. It's in Lyra. All the other stars look like it. It's cool. But Sam, why does it pulsate? That's a great question. The answer is extremely complicated, and if you want to talk to me about it later, I'd be happy to tell you about it, but it is beyond the scope of this public outreach talk because it requires having taken irradiative processes graduate class in astronomy. But I can do my best if you want to hear about it later. Basically, the gist is the star contracts, and then some really fancy stuff happens inside the star that pushes it back out again, and then it contracts, and then goes back out, and it just keeps doing this. And these stars that do this are actually nearing the end of their life. You may be familiar with the red giant stars. These are what happens when you have normal stars like our sun. They get older, they get bigger, they get redder, and they get cooler. And then eventually they fizzle out and die. And RR Lyrae stars are, in fact, they're after the red giant stage. So if you look, this is everyone's favorite Hertzsprung-Russell diagram, which shows you the evolution of stars. This line here is your normal stars. This big yellow circle is the sun. And RR Lyrae stars used to be on this main sequence, and they are now going into the giant section. They're on the instability strip. An RR Lyrae star is what's called a horizontal branch star, because if you look at it in this space, it's on this horizontal branch. This is actually a good name for once, because it is this horizontal branch. And then this star has run out of hydrogen to fuse in its core. It's now fusing helium and things heavier than helium, which contributes to the weird things going on that make it pulsate. And you have some other horizontal branch stars that don't do as interesting things as RR Lyrae, but RR Lyrae are our main focus here. So there are these very special horizontal branch stars that are post-giant. So they're, millions of years away from their death instead of billions of years away. And they are typically smaller than the sun. So these stars started at about 0.5 to 0.8 solar masses. By the time they end up as RR Lyrae, they've shed some of their outer layers and are now closer to half a solar mass. But since they're in the giant phase, they're larger. So they're at like 50-ish times the sun's radius. They're much, much larger, even though they have a smaller mass. Because giant stars, weird things happen. So this is why RR Lyrae stars do what they do and why they're cool. That was background. That's the, I hope you come away from this talk understanding what an RR Lyrae star is and that they exist. And if you want to know more about them, please talk to me later. But Sam, what are you actually doing with these stars? I've told you about the stars, and that's cool. But, my research, we already know they exist. So my research isn't just, saying, hey, this exists, it's there. My research does things with these RR Lyrae stars. So the goals of my research are to find new RR Lyrae in LSST. Now, you've, I'm sure, well, maybe, heard lots about LSST. LSST is the legacy survey of space and time at the Rubin Observatory, which is at a big fancy new telescope in Chile that's opening up soon-ish, and we'll hopefully get data from it soon-ish. And there are many, many, many ways in which it is the best telescope for time series stuff right now. The main couple are that it is by far the strongest telescope and best camera. So we get very high resolution pictures of things that are very faint. So we can look at very faint objects and see them very well. Rubin also takes a lot of pictures of things in a short amount of time relatively. And so this helps us with looking for RR Lyrae stars because they have fairly short periods. So there are many reasons why Rubin is cool, and this is just one of them. And there you can look online and see why it's incredibly cool. But we're going to find new RR Lyrae in LSST. We're going to recover information about these RR Lyrae stars. I talked about the period luminosity relationship. So we're going to find their period and then find their distance from that. And now that if we know a bunch of new RR Lyrae and their distance, we're going to be able to use them to map out some interesting things in our galaxy, like globular clusters and the halo. And maybe stellar streams, which are really cool, and are these little streams of stars that are sort of floating around our galaxy that are really hard to find because they're super faint. So RR Lyrae could help us find some more stellar streams. And maybe dark matter? This is all I'm going to say about dark matter right now, but maybe. So as I said, the LSST, the data set, does not exist yet. And so in order to make a method that can find the period of things, I had to invent data to make sure that it would work. So I used these templates. These are what RR Lyrae kind of look like. This is from a great paper where this team developed over 1,000 templates of what different RR Lyrae can look like. And a lot of them look really similar, but they give you an idea of what kinds of variability you're looking for. And so I use all these templates, and I take the templates, and I use a Python package that's called light curve links. And they don't have a logo yet, so I made this one. This is an Iberian lynx, which, side note, recently is no longer on the brink of extinction. There are now 400 of them in the wild, so good job, conservationists. And there's a light curve on it. So this is a light curve lynx. And also, it's fun, a side note, also, the light curve kind of matches the shape of this thing's legs pretty well. Anyway, this is a Python package called light curve links, and I feed it the templates, these templates, and I feed it this map. This is the Rubin Observatory's survey plan. This is what it's going to look at when and how much. The yellow region is going to look at a lot. These are called the deep drilling fields. That's really going to drill into these fields. The green stuff is like normal stuff, and the purple stuff is like, we don't really care about this. Or we don't care, sorry Jake, we don't care about this that much. Or we're doing very specific things with this, and we don't need to look at it as often. There we go. So I feed it this survey strategy, the templates, and then it spits out a light curve of what an RR Lyrae might look like. And it basically just samples from the template at the Rubin time. And you can see there are these big gaps here when the Rubin Observatory is not looking at the object, which is not ideal for time domain stuff, but Rubin Observatory is so cool and so fancy that they needed to do a bunch of stuff, and so it doesn't always do everything perfectly for you, but it's still fine. So you got these big gaps where the Rubin Observatory is looking at other things, and we have this in 4 different bands of light. These are different ways of looking at light. You can get different pieces of information from different bands. And you can also see these error bars. This is how confident we are in this specific data point. And there's this big scatter of points. This is the coolest part of this Python package, is that it simulates the scatter on the data points. So I take this data, and then I can phase fold it. Remember phase folding from earlier? This looks like garbage. You can't tell anything that's happening. And this, you can kind of see there's a light curve shape here. This is the RR Lyrae pulsation shape. So you take the data, you phase fold it. That's cool. I can generate, this is 2 years of data in a regular field. This is 30 days of data in a deep drilling field, and this is really, really faint. So 25th magnitude is just about the limit of what the Rubin Observatory can see in a single data point. And this data is really bad. This is like, the error bars are huge, and there's a big scatter. And this is kind of what it would look like. This is 30 days of deep drilling field. And this kind of looks, you can kind of, if you squint, you can kind of see a variability thing here. And so this is the main challenge. How can we recover data about stuff? How can we recover the periods about things with very small amounts of data? So what we do, to fit this data, we do a generic template fit. We assume some shape that RR Lyrae have, and we do a lot of math behind the curtain to try to find the best parameters that make that template fit the best to the data that we have. This is the equation. No, I will not be talking about it. But we get a lot of good stuff about this data. Most importantly, we get the period and the distance. And those are the 2 biggest things that we need to map out our galaxy with RR Lyrae. So, applying this period fitting method to some of our data, here is long data. You can see this is normal data. This is phase folded with the template fit. You can see the template fit doesn't exactly match the shape, but it generally matches what's going on, and it gets the period right to within a very small number. So the true period is about 0.55 days, and this algorithm gets 0.55 days. Great, we're good. But this is pretty easy, because this is like several thousand days. This is a lot of data, and so that anyone can do this. You could give this to your grandma, and she could probably get the period of this RR Lyrae. But the hard part is doing very small amounts of really bad data. So this is like 30 days of a deep drilling field. This is about 20 points and really faint information. And we still recover the correct period mostly from this really bad data. The correct period is 0.3054 days, and we get 0.3053 days plus or minus 0.0004. That's right enough in my book. This is the correct period that we've recovered from this really bad data. And you can see the fit is like, I would not have come up with this if I was just looking at this. So I was very impressed with this method that can tell us really good information about these RR Lyrae stars. Cool. So now we have the period and the distances to these RR Lyrae stars. What next? Mapping. That was the first word of my talk title. And now we're going to do mapping. Yeah, thank you. We've come full circle. This is what mapping looks like. So we basically plot every RR Lyrae that we know. We look at their distance on the y-axis. This is how far away they are. And then this is basically just where they are on the sky. This is like angle. So this is 360 degrees. And if you just look at this, you can see some patterns. You can see this fun little dolphin shape here. You can see this spike. You can see this little descending fluke here. There's some random globular clusters here. But this is the kind of thing that we are doing, is that we are plotting a bunch of RR Lyrae on a big table, and then we look at it with our eyes, which is good, and we also apply data methods to it. So like, we do some analysis of finding out which of these stars are associated with each other. Which of these stars are sort of moving in similar directions, which of these stars are in the same area, and we link them together, and we say that these are part of the same structure. And so we get different pieces. This is the Sagittarius stream, which is by far the largest and brightest stream in our galaxy. But we can use these RR Lyrae stars to actually find these streams. We already knew about this stream, but if we find fainter and fainter RR Lyrae, which is what we're going to do with the Rubin Observatory, we can maybe find new streams with this stuff, or extensions of pre-existing streams. Because RR Lyrae are very metal poor, very old, and so are streams and globular clusters. And so you'll often be able to find new things with these stars. And so that is the mapping part. I talked about RR Lyrae, I talked about our Milky Way, I talked about mapping. So I think that's it. Thank you, everyone. Are there any questions about this kind of stuff? Yes?
So that how much do these stars pulsate and grow bigger and smaller in this amount of time?
That's a great question. The question is, how much do these stars pulsate over the course of this time? So the stars, as they pulsate, they get about 5 times brighter and fainter, and their radius changes by about 2 times. So they get about twice as small as they contract, and they expand and they get to their regular size. So they started at, say, 50 solar radii, they would contract to about 20 to 25 solar radii. So they get really small and much brighter versus much fainter. So they really change a lot. Good question.
Like, they suck up all the gases and let them all out?
So the medium length answer about that process is that stars are basically always trying to collapse in on themselves because gravity wants to pull them all towards the center of mass of the star. And the chemical reactions that happen inside the star are what holds the star up. The pressure of the radiation released contests against gravity to keep the star a sphere. So something weird happens inside these stars that makes the radiation pressure go down, so the gravity starts winning, and the star starts contracting. And as the star contracts, the stuff inside heats up and gets more dense. And as it does that, the radiation pressure will increase again because more reactions happen, and every reaction will apply more pressure to the inside of the star because it is denser. And so it'll expand again because the radiation pressure increases, and once it hits a certain size threshold, the reactions will be bad again, and then gravity will start winning, and then this process just keeps going over and over again. It is very stressful for the star, but it's cool for us. Do you have a question? That's a great question. The question is, what do I mean when I say I fold the data? And so basically, I take this big long light curve. I'm just going to back up this way, it's easier. So I take this light curve, and this light curve takes place over the course of, this is about 10 years. This is 3,500 days. And I basically go through the data, and I chop it up. I find the period of this star, which is about half a day, and then I slice it every half a day. And then I take all those slices, and I layer them on top of each other. And so each point is at a different spot in this half a day period. And so when I take all these slices and put them on top of each other, I get something that kind of resembles the general shape of an RR Lyrae light curve, because this star that point is like here, and this point is like here. So they're thousands of days apart. But when you chop up this light curve and stack them all on top of each other, you can really see the shape of this light curve emerge. And that's like the conceptual idea, and mathematically, you basically just take the modulus of the day with the period, and it was basically the remainder of the period with the day, and that's your phase. Your phase. In the back. The question is, what explains the little pickup before it starts climbing again? So this is the generic shape of an RR Lyrae, and a lot of them do this little thing right here. So it has this big dip, and then it starts to go up a little bit, and then it dips again, and then it shoots up really fast. And this is there's a very long answer, which I'm not going to give. There are many papers written about that little dip. And basically, it just has to do with the way that the reactions happen inside of the star, that gravity is much slower compared to the radiation pressure, and the star starts to contract, and then it hits this sort of critical point where the radiation pressure starts to increase, but it basically hits a little speed bump where the radiation pressure stops increasing briefly, gravity starts winning again, and then it hits the real critical point at the middle where you really shoot back up in size. But the real answer is that it's incredibly complicated about why that's there. But a lot of RR Lyrae look like that.
Refer to GRIZ.
That's a good question. The question is, what does this legend refer to when I say GRIZ? These are the different wavelengths of light. So the Rubin Observatory takes pictures in several different wavelengths of light because you can find out different pieces of information about things based on what kind of wavelength you're looking at. So G is like green in the visible light. So if you looked at the star in G band, you would look green. And R is red. And then I is like infrared. These are well named. And then Z is like farther in infrared. So you could see these two really, and you wouldn't be able to see these two. But you can tell different things about stuff by what they're doing in different bands. And this helps us also fit the light curve. The Rubin Observatory actually has 6 filters, but we're currently only looking at 4 of them because of the way that they interact with each other. But it's really hard to look at the entire spectrum of light of one single object, and so this is what we settle on to try to find out stuff about one thing by taking like just a couple pictures. Yeah.
You said that library are small. So I'm assuming that the word is so here's the branching out with between, I guess, when they decide to our library continue on the sequence.
Yeah. The question is, what is the point at which a star will either continue on down the normal star path versus become an RR Lyrae star? And so if we go back to the Hertzsprung-Russell diagram, you can see, so there's normal stars go to this horizontal branch. This is a normal stage in a star's life cycle, and it is just very specific masses and radii and compositions of stars that become RR Lyrae. Because these stars are old and metal poor, they have sort of interesting reactions that happen, whereas newer stars that get made have more metals inside of them, and so they don't necessarily have these reactions. So all stars go through this, well, most normal-sized stars do main sequence, then giant, and then the horizontal branch, then there's the asymptotic branch, and then they basically die after that. So all stars do the horizontal branch, but you have to have very, very specific compositions and size to be an RR Lyrae.
Green, red, and like infrared. How come we don't see more like green stars? Because whenever you look, it's usually between like red and blue light. Like I never see like green.
Yeah, so when I was talking about the bands of light, I mentioned G is green. And so the question is, why don't we see like green stars? And this is actually because of the units on this plot, green is actually the lowest of these bands, of these wavelengths. And so most stars are actually dimmest in green. But most stars also produce light in every color, which is why most stars look white to us, because they're producing light in every color of the wavelength, every color of the spectrum. And they just, if we split it up like this, we can see, some kind of subdivision. And since these stars are red giants, they're redder, and so the red wavelengths are much more prominent. But in very young, bright stars, the blue wavelengths are much more prominent. Yeah.
So, observational question. On the slide that you explained where the RR name came from, in that field of view, there's tons of stars. How is that one mapped to the Lyrae constellation? Why is that
Right.
selected out of that?
So this question is more of an observational question about the Lyrae field. Why is this star that's not actually in the constellation, not actually in Lyrae, end up as being attributed to this constellation? This is because the constellations have like a shape, like that is Lyrae, but they have a sort of sphere of influence around them. And if you're in a constellation's sort of sphere of influence, then you're associated with that constellation. And it is basically just like where it looks like it is on the sky. So like there's no other constellation closer to RR Lyrae than Lyrae, because not every star in the sky is a part of a constellation, and they're just the brightest stars in the sky. And so they each just have a sort of circle around them, that the stars in the circle belong to that constellation, and then the next nearest constellation will have other stars in it. So the constellations actually do change over time very slowly as we orbit around the Milky Way. And so throughout the course of human history, the constellations have changed. But generally, they stay roughly constant on human timescales. All right. If you have any more questions, you can come talk to me afterwards. I am out of time, unfortunately. Thank you all for listening, and get ready for the trivia answers and the next talk.
Let's switch the trivia answer. All right, thank you again, Sam, for that awesome talk. Next, we're going to talk about our trivia answers. Pull it up. Yippee. All right. So for our first question, our trivia answers were from how RR Lyrae stars are primarily found in which stellar populations. Sam told us it was old Metapore population 2 stars. And then why are RR Lyrae stars especially useful for mapping Milky Way? It's because there is a direct relationship between their period and their luminosity. And then they typically have pulsation periods of on the scale of hours to about a day. And these RR Lyrae stars are most commonly found in the galactic halo in the galaxies. And if a RR Lyrae star appears fainter than expected, it's because it is farther away than we thought it. And the boundary between asteroids and comets is best described as C, a distinction based on volatile content and activity. And 7, an object classified as a near-Earth asteroid must have a perihelion distance less than 1.3 AU, where AU is the distance between the distance scale between the sun and the Earth. And then 8, the primary long-term threat from a large asteroid impact comes from C, the global climate effects from dust and aerosols. And then 9, many asteroid impacts are avoided because C, most near-Earth objects are small and burn up in the atmosphere. And 10, modern asteroid surveys improve detection efficiency primarily by a larger telescope mirror size. All right, so we have a tie for second place with 7 correct answers. And that is our team Mark C. Nice. And the former folding chair crowd. Congrats. And then our first place winner with 8 correct points is team JHS. Who's that? Nice. All right. We'll have prizes for you guys at the end of our second talk. So now we're going to take a short break just to switch our computers, and y'all can take a second to grab some snack or another beer, and then we'll be right back. All right. Thanks, y'all.
Yeah.
All right. So our second speaker of the night is going to be Dr. Michael Solontoi, who is a professor at Monmouth College, who did his PhD here at the University of Washington. And he studies asteroids, which, based on his title, I think he might be telling us about some today. All right, take it away.
The right distance to hold this from. Good. Outstanding. So before we get going here, this is Killer Death Rocks from Outer Space, which is my highly professional title. But before we get going on that, I wanted to mention one thing. I added this while Sam was talking because I saw his picture of the Milky Way up there. And that whole thing within the middle of the Milky Way, the bar, how it isn't just like a ball anymore, that happened while I was taking my galactic structure course at the University of Washington. So that comes to this right here. This is the greatest thing about being an astronomer. As I wake up every morning, it's like, what won't I know today? If I'm not wrong, like being wrong for the right reasons is fantastic. If I'm not wrong about 3 things a day, I'm having a bad day. Not like things like, does red mean I should go on the stop? But you know, like, you know what I mean by good things. Anyways, so let's go back all the way to the beginning. In the beginning, there were people. And there was the sky, and people looked at the sky. And actually, people were probably looking at the sky long before they were even people. I mean, you know, our curiosity of the sky probably outdates our own identification as Homo sapiens. So it's been with us for the whole of, well, ever. And to be perfectly honest, it was our companion for a lot of years. And once we got kind of technologically, you know, feeling our oats and things like that, we started creating technology to help us investigate the big black above us. We developed telescopes to let us see far more than what our biological eyes would let us see. Let's built rockets to actually go there and throw robots and people and Tom Hanks out into the solar system to investigate things and say pithy comments to Kevin Bacon. And in the process of this, we spent a lot of time sending rockets with telescopes to visit these. These are the planets of the solar system. We're not talking about these guys. They get enough press already. We're going to talk about the rocks, the stuff left over, the stuff that never makes the big screen unless Bruce Willis needs to blow something up. These are typical asteroids in our solar system. These are all asteroids that have been visited by spacecraft. That's Lutetia. It's about 100 kilometers across, and the others are far, far smaller, ranging down to the little thing that looks like a pixel up there. That's the asteroid Itokawa. And Itokawa is kind of cool because we actually have dust from Itokawa. Japanese spacecraft landed on it, statically collected a couple pieces of dust and brought it back to Earth. There are some larger asteroids. We've visited the largest asteroid series, about 1,000 kilometers across, and apparently my animated GIF is not playing. GIF, 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 GIF. But Vesta is, and Vesta is about 600 kilometers across, depending on how you measure it. Depending on how you measure Vesta, it's either the 2nd largest or 3rd largest asteroid, but we don't really care about like numbers and rankings and things like that. Despite how big these things are, and Ceres is starting to look a lot like a planet. In fact, if I told you, like if I lied to you, just showed you that, it's like, oh yes, that's Mercury, you might believe me. I wouldn't actually do that. But all these things are far, far longer than our old friend, the moon here. So they're very, very small objects, and they're all interesting in their own right. And for the most part, they live in our solar system here. All those little blue dots are grossly enlarged positions of asteroids on one day from back in 2006 when this plot was made. I've highlighted the orbits of Jupiter and Mars, and for the most part, they live in this big, big donut of asteroids. Millions and millions and millions and millions of them. We know of about 1 million of them today. There's also a cluster of them 60 degrees behind and 60 degrees ahead of Jupiter in their orbit. These are the Trojan asteroids. Monmouth College is a small liberal arts institution, so this is the liberal arts education portion of it. They are the Trojan asteroids because many of them have names of the heroes of the Greeks and Trojans from the epic of Homer, the Iliad, and then following up the Odyssey and everything else. For the most part, the leading cluster are named after the Trojans. The chasing cluster are the Greeks, so the Greeks are chasing the Trojans around the sky, except for Patroclus and Hector, who are in the wrong cloud, so they're traitors. But wait, there's more. It's not just rocks out in outer space, it's also chunks of ice, or at least rocks with a bunch of ice. The biggest change, and I didn't know that when I started doing this, is that in recent time we've taken this idea that comets, which this is, aren't dirty snowballs, but they're more icy dirt balls, really. But essentially, if an asteroid has enough volatile material in it, we can call it a comet. Now, it's actually pretty hard because unless we throw it close enough to the sun that it starts looking like that, it's kind of difficult to judge volatility from like way off in the distance. Some nice pretty pictures of comets. These are some pictures of some great comets from the past few decades. We've got everybody's favorite. I think there's Yakutaki's in there, Hale-Bopp's in there, Holmes is in there, West is in there, Mackholtz is in there. At one point I know which one was which, but now they're just all just very pretty. And we've thrown robots at these as well. So these are cometary nuclei that have been visited by comets. The 1986 apparition of Halley's Comet, there was a whole fleet of spacecraft that visited it, and it by far is the largest cometary nucleus that we've observed, or not observed, but visited up close like that. Hale-Bopp's nucleus was estimated to be somewhere between 40 to 80 kilometers across and would absolutely dwarf everything on here, but we didn't throw robots at it. I insulted robots too many times. Oh, there we go. We're back. Cool, cool. Where the comets come from, they have to be someplace colder. If they actually lived out in this donut-y region between Mars and Jupiter, they would quickly devolatilize and they wouldn't be comets anymore. Much like the asteroid belt, there's a second belt, the Kuiper belt, which lives out beyond the orbit of Neptune. It is a nice cold reservoir where a lot of the comets reside. That doesn't explain all the comets, however. Comets, particularly like things like Hale-Bopp, just come in from out of nowhere, blow by the sun, and then go away and never return, sort of like bad house guests. They have to come from further away. They come much, much further away from a structure that we have barely seen any in situ. That means like actually there, objects in the Oort cloud. You know, the ones that we do are very tenuously labeled as very, 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 very inner Oort cloud objects. But this is a region not just out beyond the orbit of Neptune, but it really starts in earnest at about 10,000 astronomical units. So that's 10,000 times further away from the sun than the Earth is. And it extends out maybe as far as 100,000 AU, which is about a third of the way to the nearest star. So that's pretty extensive. And at that point, the sun is pretty feeble in terms of everything it does. And these comets can actually be way out here, perturbed around just by passing stars or even just the tides of the galaxy, which is ridiculous. Now, this was kind of a crash course introduction to these things, and since I'm talking about it, and I'm very, very, very excited about it, why? Why am I excited about these things? Well, I'll give you the practical answer first, and this is what gets us funding. Sometimes space interacts with us. This is the bit of space that actually could potentially affect our lives someday. I'm sorry, I don't think there's an RR Lyrae that's gonna, yeah, no. Yeah, but this could ruin our day. As long as we keep the right people scared about it, we keep getting funding, so, all right. But no, seriously though, take a look, here's the moon. What do we notice about this picture of the moon? What sort of features do you see on the moon here? Craters, big round things, yeah, craters. Every single one of these little round features and big round features and medium round features on the moon represents a big chunk of real estate that slammed into the moon at orbital velocity. And the Earth is larger than the moon. The Earth has larger gravity, and it's kind of impossible to think that I could throw a bunch of gravel at the moon and not hit the Earth. And if we do a little bit of scratch math on the back of a napkin, you can come up with that for every one of those holes on the moon, Earth should have picked up 10 of them. Now, we don't really see them because water, oceans, and earthquakes, volcanoes, all of the land on the Earth is ridiculously young compared to anything in the solar system. But anything that's happening to the moon is happening to the Earth 10 times over. And indeed, it does. This stuff hits us all the time. Most of it in terms of little teeny tiny flecks of nothingness. Particles on the size of smoke to sand to grit. We call it dust. When an astronomer says dust, we're really thinking about something not that you find under your bed, but much more like cigarette smoke level things. But these particles rain down on us all the time. We go through them. We pass through debris clouds left behind in the solar system. We see them as meteor showers, meteor storms, shooting stars. Every now and then we'll encounter something a little bit bigger. And it'll punch down into the lower atmosphere and explode with a nice kaboom. This is a very entertaining kaboom because it happens far away from us. And when this kaboom happens, properly speaking, this is called a boloid. People will also just call them fireballs. So, you know, fireball. All right, yes, excellent. My obligatory D&D joke. Look, Star Wars, D&D, and Marvel Comics are like mainstream cool now. I'm living my best 80s child nerd life, okay? All right? I was the Stranger Things kid. Okay. But the other cool thing about this is that this is free delivery of extraterrestrial materials. When these things explode in the atmosphere, some of the rocks survive, some of the rocks will make it to the ground, and these rocks are meteorites. And they are fantastically important because these are the oldest rocks we will ever find on the Earth. These are rocks that formed in the early part of the solar system and have done nothing for 4.5 billion years, as opposed to the rocks on the Earth, which have been melted and volcanoed and earthquaked and plate tectonic to, gosh, brand new configurations all the time. For example, this was a boloid that was seen over Northern California back in 2012. And I put this in here again because I teach at a liberal arts college in Sutter's Mill, California. American history quiz. Why might you know about Sutter's Mill? Yeah. That's right.
California.
Absolutely. That's where the California gold rush began. So that's why I picked the Sutter's Mill one out of that. But we find these things all over the place. And every now and then, something even larger. Also right about then, 2013, Chelyabinsk, a city over Siberia. Another fun historical fact, Chelyabinsk is the region of Siberia that the Soviets moved all their industry when the Nazis invaded in Barbarossa. They packed up all the tank factories from Moscow and shipped them out to Siberia. But this was something probably about a 20-meter rock flying through the atmosphere that detonated over the skies of Chelyabinsk. And this was a big enough kaboom that you start going, oh wait, this isn't quite so funny anymore. The rocks didn't hurt anybody, the kaboom didn't hurt anybody, but Chelyabinsk isn't really built on like an earthquake-proof zone. So about 1,000 or so people were actually injured to the point of seeking medical aid, typically by broken glass, falling awnings, things from when this big kaboom happened and just shook the city. So now we're starting to go, oh, hold on, this is getting a little bit interesting. And then we can find things like this. 50,000 years ago, blob of iron about the size of a school bus slammed into what is now northern Arizona. This is Barringer Crater or Meteor Crater, Arizona. It's about a kilometer across, little visitor center, see the little cars there for scale. This is probably the best classic looking crater on the planet. Like this actually looks like a lunar or a Martian crater, simply because after 50,000 years, Earth has not had a really good job of scrubbing this blemish clean yet, as it has for so many others. And then as we get larger and larger and larger, you come across this little brown strip of rock there, right between the bright white rocks of the Cretaceous full of dinosaur fossils and the dark rock of the Tertiary containing no dinosaurs. Because yes, this is the KT boundary, and 65 million years ago, we need to give thanks to the dinosaurs who bravely laid down their lives so that our squirrel-like ancestors could go on to repopulate the planet in their absence. Now, this does, we're laughing at it, but we don't really want to go the way of the dinosaurs, so we've been hit in the past. Bad news. We're going to get hit in the future. We just are. Legitimately good news. We don't know the single rock that's going to hit us in the future that we really have to worry about at the moment. That's not to say that they're not there, But by the way, this is from a Saturday morning breakfast cereal. My caption got cut off down here. Fantastic, fantastic webcomic. And there's no conspiracy to hide an incoming asteroid from you. If there was an asteroid coming towards us, all of a sudden planetary science would get the military's budget. And we're bad at keeping secrets already, okay? I mean, we just are, right? I mean, okay, yeah, you're not, yeah. We're terrible at secrets, righto. But there's a lot of them out there. This plot, generated by the Jet Propulsion Laboratory on Monday, there is, as of right now, about 40,000 near-Earth asteroids. These are not necessarily hazardous asteroids. These are just ones that, as per the quiz, come within 1.3 astronomical units of the sun. Most of them are in this blue here, which is just all of them. Most of them not too worrying about. These orange ones, we start to get concerned. They're on the order of 140 meters across, which isn't like KT size, but it does have a very interesting size in terms of how much energy it can deliver to the Earth. Go back to when you were a kid and you're in the bathtub because your parents made you take a bath, and you start sloshing back and forth. What happens to the water if you slosh back and forth in the tub at just the right rate? It gets higher and higher, and eventually you can send all the water out of the tub onto the floor, and then your parents are really happy with you. Turns out somewhere around that size will do that to the oceans, or could do that to the oceans. So bad. That would actually be better to land on land than, say, in the Atlantic or the Pacific Basin there. But regardless, oh yeah, I forgot that I added this. This is just yesterday, 4 rocks came by us. 2 of them passed just outside of the moon's orbit, and 2 of them actually passed within the moon's orbit there. They range in size from about 2 meters at the smallest, so 2 to 5 meters, up to kind of 25, 30, 40 meters. And if you notice, their names all start with 2026, meaning we basically discovered them right about the time they flew by us. And there's a reason for it. This is a 5-meter rock. It's about the same color as a charcoal briquette. I don't care. Put that, far away from the sun and point the Hubble Space Telescope at it for 5 days straight. You just wasted a whole lot of research time and you never actually saw it. These things are just too faint to track and identify unless they're just ridiculously close to us or we get ridiculously lucky about it. Also, in terms of predicting an impact, it's hard. We are computationally limited just by numerical precision. And how accurate do you have to be? Well, kind of rule of thumb, you gotta be within about 7 minutes accuracy to really predict a collision or not, because the Earth, we're hauling through space. The Earth moves an entire Earth diameter every 7 minutes. So, you gotta be pretty accurate. Right, okay, how do they get there? We're done with the scary part of the talk and into getting closer to doing some science now. How did they get here? Because we already talked that they all kind of live out in these lumps by Jupiter or in this big donut between Mars and Jupiter. Well, the answer is, sorry, I always do that. Whenever I have the lapel mic on, I always do that. Jupiter. Always blame Jupiter. If something is weird in the outer solar system, just blame Jupiter. You're probably going to be right. If not, Jupiter will be involved, even if it isn't the answer there. So looking at this plot, other than the fact that, hey, they're kind of inside the orbit of Jupiter, we don't really see something that's pointing towards Jupiter being the culprit here. But if I wave my magic science wand, and instead of making that plot that showed where all the asteroids were on a given day, I show you where they are on average, all of a sudden the asteroid belt looks like it has some structure to it. Ooh, science likes structure. We see gaps, we see asteroids, no asteroids, asteroids, no asteroids, no asteroids. If I plot this up in a histogram, I know I just made a plot in a public outreach talk. I'll get stuff thrown at me later. It's fine. Number of asteroids, distance from the sun, asteroids, no asteroids, asteroids, no asteroids. And these locations where there are no asteroids are places where the asteroid's orbit passes by Jupiter at the same place in the orbit again and again and again and again and again. Meaning Jupiter gives it a big old gravitational kick in the same way at the same place in its orbit over and over and over and over again. And it quickly depopulates any asteroids that happen to wander into those gaps. To kind of see this in action, this is a simulation of an asteroid's orbit. That's the inner solar system, and then Jupiter out here. The red line is where the asteroid starts, and the blue line is what we call the osculating orbit. This is just the orbit due to the fact that, you know, Jupiter and Mars and all the planets are going around, kind of bumping it around a little bit gravitationally, but you notice it just sort of hula hoops around. It doesn't wander away very far. So overall, the red line is still a pretty good description of its orbit at any time. Now, I'm going to restart this, but place it in one of those spots where it encounters Jupiter over and over and over again. Oh, it's already doing bad things. Life is better with sound effects. And all the dinosaurs die. Right? So we can see quite quickly, in just a handful of millions of years, which is what the clock is running in the upper left there for you, Jupiter manages to kick this thing out of the asteroid belt and into the inner solar system. So fantastic. And actually, we are straying very closely into doing some science. So let's go ahead and just keep rolling with the science. What I'm been talking about here is kind of dynamics and astrometry. Astrometry is knowing exactly the precise location of something, and the dynamics is how its orbit is going to change in time. So basically, it's very accurate observations combined with very accurate physics. For example, this is the asteroid 1627 Ivor, not Hagelin, which I just realized I picked Ivor and I'm in Seattle, so that's kind of cool. A couple of people chuckled. Okay, good. But I observed Ivor over the course of 3 nights. I was able to then do some fancy 6-dimensional geometry to it, and I was able to produce an orbit of Ivor. Large scale for the dynamics, we've got this. Now, why am I showing you a picture of rubber duckies? Has anybody heard of the friendly floaties? All right. Well, if you haven't, today is a wonderful day, because today is the day you learn of the friendly floaties. In 1992, a cargo container went overboard in the North Pacific. This cargo container was full of bathtub toys. These bathtub toys have been circling the globe ever since. Within months, they were washing up on shores, and within a decade, they reached places as far away as Scotland. And this accident was a boon to oceanographers in their ability to study and map the ocean currents and how the ocean currents were connected to each other. And in a real way, the asteroids and comets, the small bodies of the solar system, are our own friendly floaties. They aren't the big ones. They aren't Jupiter, Saturn, Neptune, Uranus, but they do map out where the solar system has places of stability, where it has places of instability. And if you want to puzzle out how the solar system got to the way it is, it's our friendly floaties, the asteroids, that are going to put any constraints on your theories of how the solar system formed and evolved. Looking at the solar system, there's all sorts of problems with where the planets are today. It makes no sense at all. Like, Neptune shouldn't have had enough time within the lifespan of the universe to have formed where it is. So clearly, the answer is to form them where it makes sense and hope gravity does some noodly-doodly nonsense to them and puts them where they're supposed to be. Well, if you want to test if your noodly-doodly nonsense is better than someone else's noodly-doodly nonsense, then you'd better reproduce where all the asteroids are. And it's not noodly-doodly nonsense. It's absolutely beautiful bits of celestial mechanics and dynamics, and I love it a lot. I only ever really make fun of my own work. The other thing that we're doing here is that in various populations, we classify them, because science, like my rabbit, loves classifying things into boxes. That's a big part of science. We make boxes, we classify it, and you know what? The boxes aren't always right, but they're a good start. So here's a slide I stole from the rock and roll world of geology. How do you know that these are different rocks? It's a real easy, simple answer I'm fishing for, which is they look different. They have different colors, right? That's how we know they're different rocks. They look different. Well, as silly as that observation stands, that's going to apply to asteroids also. An asteroid made out of one mineral is going to it's going to reflect light differently than an asteroid made out of another material. So one way of classifying asteroids would be to observe them with a telescope. And just like Sam was talking about, you look at the asteroids through a number of filters. We can kind of work out the difference between some of these filters, and we can crudely divide up the asteroids into 3 different types of asteroids. Asteroids that look like big balls of carbon, asteroids that look like rocks, and asteroids that look like basaltic rock. Basalt, just go down to the basalt, I really do mean what's hanging out on Mount St. Helens, which to date myself, I remember the eruption, and I remember brushing ash off of my dad's sweet, sweet Camaro at the time. Beyond this, if you want to do a better job of classifying, we need to take spectra. We need to take a look at the light reflected from the asteroid, break it into a rainbow, and measure the intensity of the light at every wavelength. And then we can plot it up, and yeah, this was a very, very faint asteroid that Zach Betterton and I were observing. But when we observe it like this, then we can start fitting templates to the spectra to try to figure out what it is. And this is somewhere between what we now have an SQ and a Q type. The letters are kind of mean. S sometimes stands for silicate, but yeah, astronomers still name things poorly, regardless of which subfield you're in. Okay, but yeah, we have all these different templates of different types of spectra for asteroids, so we can assign these spectra to different templates. We can do even better than that. Remember, we also had rockets. So if we strap a camera to a rocket, we can actually do this same thing to different units, to actual bits and pieces of the surface. This is a picture of the surface of Vesta taken by the Dawn spacecraft. Dawn was equipped with a whole bunch of really nice geological filters. So some work a student of mine did, all the different colors represent different mineral concentrations on the surface of Vesta. So now we're not just looking at the bulk composition of an asteroid, we're actually doing like geological mapping of an asteroid. So that's kind of cool. And this is super important because the asteroids never got very large. Very few of them melted hardly at all. In fact, some of the asteroids, the smallest of the asteroids, really are what you would get if you took the sun and squeezed all the gas out and sort of made a dirt ball out of what was left over. So if you want to study just like the orbits of the small bodies of the solar system tell us about the origins and evolutions dynamically of our solar system, the compositions of the asteroids is really our only clue into what the solar system looked like chemically in the very, very early days. And there would be, it'd be remiss to give a Astronomy on Tap talk in Seattle if I didn't bring up the Rubin Observatory. And beautiful thing about being attached to a major observatory is that they put the funding logos on the slides for you, so you don't have to remember and you don't accidentally forget to credit somebody for something. The Virasi Rubin Observatory and the forthcoming Legacy Survey of Space and Time. What is it? In a nutshell, it's what you get when you combine a 27-foot wide mirror with the world's largest digital camera. So it's a digital camera with about 3.2 billion pixels on it. Something, what, like 400 Ultra HD TVs to display. I don't know the new number. I remember the old were just high definition TVs. It took 1,400, but TVs have increased. Mount both of them in a 300-ton telescope that can turn all the way around in about 9 seconds. So this thing's fast. Put it into a mountaintop fortress. Seriously, the Rubin Observatory building, all I gotta do is like write, property of Lex Luthor on it, and it's like an anti-Superman laser coming out of it or something. It's a survey. It's gonna observe the night sky and produce a database about 500 petabytes, which is mind-boggling for science, and a project that involves thousands of people. I think several of us, so. In a nutshell, what is it? Rubin, it's going to basically try to image the entire southern sky in 6 filters about every week for 10 years. So another way of thinking about this is that Rubin is going to reproduce an entire modern astronomical survey every single week. And that's going to allow you to do some of this wonderful time domain stuff that Sam was talking about. You're going to be able to observe asteroids over 10 years. You're going to be doing all sorts of fantastic things with this instrument here. And basically, the way I like to describe the strategy of LSST is just observe everything. Observe everything and let people sort it out. And that's really what we're trying to do, because quite frankly, I believe probably the biggest scientific discoveries that are going to be made with Rubin and LSST haven't even been thought of yet, even from people who've been working on this thing for 20, 25 years. In my own field, the solar system, what are we looking to do here? Well, I'm going to steal this beautiful public video that was put together off of the first look, that just in the first look kind of press release, they discovered, not observed, but discovered 2,000 asteroids in just a few nights of operations. That's pretty impressive. We're expecting to find on the order of 5 million main belt asteroids. That's discovering 5 new asteroids for every 1 asteroid we currently know of. The other way I like to think about this, think about every single picture that has ever been taken of an asteroid or comet in human history. In 10 years, we're going to take 20 times that number. That's just absurd. Absolutely absurd. Is that number still correct?
A little lower.
It's a little lower. People have been taking pictures for a lot longer than now. So, but yeah, okay, change it to 10. It's still order of magnitude correct. So by observing everything, it gives you a chance to observe really, really rare things. And one of the rare things, these are things like asteroids that have outbursts due to little collisions, comets that are hiding in the main belt, and interstellar interlopers. So I'm going to end with kind of the when the rest of space interacts with the solar system. These are images of the first 2 interstellar comets that were confirmed, 1I Oumuamua and 2I Borisov. These are, just like our solar system will kick asteroids far out into the galaxy, well, so does every other star out there. So as we zip through the galaxy, we are going to encounter comets from other stars. And that's what these 2 were. And over the summer, I had the opportunity to join forces like Voltron with about 250 of my close friends and write a paper that may or may not be the first science paper that used the full-on 3.2 gigapixel camera for a science result on observations of the 3rd interstellar comet, 3I Atlas, which was discovered by the Atlas survey, and we quickly realized that it was traveling right through the fields that Ruben was using to commission said ginormous camera. So this was pretty cool. I was actually on vacation with my wife in Jamaica, and we got the call to arms. So I was like, honey, I got to do some work, but it's super cool. And she's like, no, that is super cool. Go right ahead. And I did. I even made it above the fold. So I'm actually above the plus 112 additional authors line there. So it's pretty cool. Anyways, what I'd like to say is that beyond the ability to observe everything allows you to really observe anything. And I encourage you to go out and observe anything and think about anything, but especially asteroids and comets. Thanks. I don't know, timing for questions, or if there's, if there's a couple questions, sure. What's happening? I flummoxed you. Yeah.
So the Rubin Observatory, it sounds like you've both been, maybe I'm misunderstanding, but it sounds like you've been talking about data that's been coming from it, but also it's gonna open and it's really cool.
Yeah.
So has it opened? Is it open? Is it getting refurbished?
A little bit of everything except the refurbish, because it's still brand new. So I guess it'd still be optimized. So a lot of the early data, people have been working with Rubin for a while. So I have been, the way I describe it until recently, I've been observing fake comets with a fake telescope producing a fake survey. So I've been doing things with Rubin since about 20 years now. So that's how long it takes one of these major projects to get going. And the folks who actually designed it were working on it well before me. Rubin, so what is available and people are doing things with is the commissioning data, which was using a smaller version of the main big camera that was designed to test it out. They pointed at a number of fields, and there have been a number of science papers, actually a lot of science papers written on that data already. The Atlas thing was kind of a special thing. We got kind of permission from various agencies to work with it because it was such a timely, big press type of event there. The LSST survey itself is scheduled to begin soon. That's all I'm going to say, rather than making up a date and being completely wrong on it. But it's going to start very, very soon.
Okay, so like the telescope has been there for a long time and they're starting a new project.
The telescope is brand new for basically the telescope was built for this project. So yeah.
Within the last week or two about a comet that was spinning and then it stopped and started spinning the other way.
Yes, actually I have.
Where does that come from?
All right, the question is that there was some sort of news report of a comet that was spinning one way and then it reversed its spin. I've read this. It's on what we call our preprint server, so it's still being reviewed. The author of that paper, Dave Jewett, is like one of the big names in comet science. So I trust that he's not making it up. The idea is this, and I can kind of see, we've definitely have seen every comet is spinning. And when comets start melting, start evaporating, they don't evaporate away uniformly. There's bits and pieces, so they come off like little jets. And this is one of the reasons why studying comets gets a little bit difficult, because they don't follow a nice, beautiful orbit via Newton's second law, just with gravity. They also have these little jets. So you can imagine it's more like a well-thrown knuckleball. You know it's going to get to the catcher, and you know it's going to be roughly in that area, but you're not really sure exactly where it's going to be. They're also spinning. So you can imagine that as a comet is spinning, if it has some of these jets angled at the right place, as they turn on, they're going to slow that motion down. And then they could actually then start spinning it the other way. And we observe a lot of comets changing their spin states. Well, not a lot of them. It's really hard to make these observations. But we do see comets changing their spin states. So it's not completely unheard of. But yeah, it's a brand new paper. I think it came out last week. And it's actually on my pile of things to read. I think it's a long period comet, but I don't know. Like I said, I'm going to plead ignorance because I got the paper and I still need to read it. Yeah. All right. Yeah.
You had a picture of the moon
Mm-hmm.
and an asteroid that was big. Was that to scale?
Yes.
Because that looked really big.
Yeah. That was the largest asteroid. So the question was, like, way back here, if this... Again, life's more fun with sound effects. Almost there. Come on. Yes. These are to scale. So this is the moon. This is Ceres, but keep in mind, Ceres is by far the largest asteroid. The next largest asteroid is either Vesta or an asteroid that's almost the exact same size of it. And then there's a handful of asteroids that are about the size of Lucretia up there. Most of them are like these ones and even smaller. Kind of a rule of thumb, for every asteroid you find, there's about 10 asteroids that are 3 times smaller. So, I mean, you know, it also just goes back, this is just a collisional process, right? If you were to, please don't, because we really appreciate the brewery here, but if you were to drop your glass, are you going to wind up with more big pieces or lots and lots of little shards? Yeah, so it's related to the same sort of collisional fracturing process. And nature just likes to make lots of little things for every one thing. I mean, are there more elephants or ants? Yeah, you know, little stars or big stars? Little stars, yeah. So it's something that we see throughout all of nature. But yeah, no, all of, at least at the beginning of the talk, the pictures here are as to scale as either I or the people who made these images at the Planetary Society were able to do. Yeah. Oh. All right. Awesome. Happy to answer. I desperately need to have something to drink, but I'll chat with you in just a sec.
That rockin' talk. And both of our, thanks to both of our speakers today and all of y'all for coming out to listen to some awesome astronomy. And if you are, we've got more coming towards you. Next month's talk will be on March 25th. So once again here at Stoop Brewing, which is our long-term location. So tell your friends, tell your family, and come out here for some more astronomy on tap. Thank you all. And if you won a trivia prize, we'll have some for you. So thanks again for coming.